So far we've discussed momentum as a vector in a linear direction, but it's possible for a collision to undergo a two-dimensional change. And so for this activity we're going to use a frame of reference where this direction is positive y and this direction is positive x. And just a quick reminder, P is mv as a vector where the momentum shares the same direction as the velocity. If we have a system where we have an interaction like a collision, the total momentum of the system before is equal to the total momentum of the system afterwards. But individual objects can undergo changes in momentum, also known as impulse. And the change in momentum is a direct function of the force times the time frame in which the impact is able to act. The example is a typical billiard collision where I have one ball moving with an initial velocity, the second ball sitting stationary, but instead of being in a perfectly straight line, it's actually offset just a little bit. And so when the collision occurs, ball number 2 actually moves off on an angle theta at v2 prime with some new momentum that actually carries it in a diagonal direction. And then the question would be, what happens to ball number 1 after that collision? Now, of course, you can probably predict what would happen to ball number 1, but we want to break it down into steps so that we can solve for that conclusion rather than just immediately assume it. So the key to two-dimensional problems really is going to be the organization of the system, right? And so the first thing I want to do is I want to take all the vectors that I see on my problem and separate them into the x and y components of that individual system, right? And so as you get better at this, it will make sense to do this directly on the problem because we see that this is an x component pointing that way, and then there would be a y component pointing vertically upward this way. Now, if I use the velocities, right, that may be useful as a conclusion, but remember that this is momentum. So before I do anything with this, I actually want to know that I need to remind myself that this should be a triangle of momentum, not velocity. So before I do anything, I either want to calculate m times v and rewrite it here, or I want to transpose this entire diagram lower and bigger so that I can work on it, right? And so I'm going to leave ball number 1 and 2 the same on this side, and I'm just going to take this picture and draw it a little bit bigger down below without the ball so that I can see what's happening. And so here is this angle theta offset like this, and I know that P2 prime is equal to M2 times V2 prime, whatever those numbers would be. And I would calculate that ahead of time before I continue with this work, because this vector now represents momentum, not velocity. And momentum is the thing that's conservative, and so that will be the thing that matters from one side of this problem to the other. And so then ball number 1, we're expecting to have some momentum that will probably be something that looks like this, where this would be P1 prime. Now, before we can get to what this final solution is, we need to go back and isolate x and y directions on this picture like I drew up here, only we're actually going to solve for them. So here I'm going to draw this in as P2 in the x direction, and I'm going to draw this in as P2 in the y direction. Now these are both primes because this is the after conclusion, right? And so then, of course, using the information that was presented in the problem, which was the velocity of ball number 2, I calculated the momentum of ball number 2 after the collision by multiplying m times v, and then I'm going to calculate P2x and P2y by doing trig functions, right? And so in this case, P2x is adjacent to theta, P2 prime is the hypotenuse, which means that P2x prime is equal to P2 times the cosine of theta. Similarly, oh, and this is P2 prime times the cosine of theta, of course, because everything is happening on the after side. So then the other direction, P2 prime in the y direction, is opposite the angle, and P2 prime is still the hypotenuse, which is the known value, so P2 prime times the sine of theta. And so now I have values for P2x and P2y prime, right? right, which are all the values on the right-hand side of this solution. So if I go back to the original problem, what I need to recognize is that the problems work exactly the same once I've isolated x and y directions. So separating into the x directions, but still treating it as a conservation of momentum problem, we have two objects and it's an elastic collision, which means that we have a P1x and a P2x prior to the collision. After the collision, because they're still two separate objects, we have a P1x prime and we have a P2x prime. Now in this particular example, P1x would be M1V1, which is given, and P2x would happen to be 0 in this particular example, but you can imagine it wouldn't have to be. This would be equal to an unknown, remember, because we do not know the momentum of P1. So P1x prime is an unknown, and then of course P2x prime is the value that we've calculated above up here. This is a known value, this is a known value, this is an unknown value, and this is a known value. And so through the x analysis, right, where as a system we've identified the total momentum of the system in the x direction and the total momentum of the system in the x direction afterwards, which if you wanted to, you could start with px equal to px prime and think about it as a conservation from here working down, where I've kept x subscripts on everything, right? It might even be useful to put x subscripts onto the velocities if necessary. That allows me to solve for P1x prime. Moving down from there, of course, is that, of course, we also have a y direction. So if I flip this over, we can do a very similar analysis in the y direction based on an elastic collision. And now the setup's going to be the same. The total momentum of the system in the y direction is equal to the total momentum of the system in the y direction after the collision, right? And so again, the setup is the same as we were doing in linear, only now I'm thinking about it in y components only. And so I would say that P1y plus P2y is equal to P1y prime plus P2y prime. Now again, in this particular example, we know that P1y is 0, and we know that P2y is 0, right? And so these are two known values that happen to be 0. You can imagine that there will be setups where they are not. Then, of course, on this side, P1, remember, is our unknown, and we're looking for V1. But in the y direction, we also don't know that solution yet. So P1 prime is the unknown in this particular conservation. But then we do know P2 prime y, because we solved for that earlier when we separated the vectors in the triangle. So that allows us to solve for P1y prime. Once we've solved the individual conservations in the two individual directions, we will have a value for P1x and we will have a value for P1y, both primes after the collision. What you'll find in this particular example is that P1x is a positive value and P1y is a negative value. Adding those by drawing them head to tail, meaning I draw the first one and then draw the second one, which can be resulted this way, or draw the first one and then draw the second one, I'll get the same resultant, P1 prime, which is the diagonal vector pointed down like this. So now I know what P1 prime is in the x direction, and I know what P1 prime is in the y direction. I'll know these values, and I'll be able to solve for P1 prime, which of course P1 prime can easily be solved for by simply just doing P1 prime squared equal to P1x prime squared plus P1y prime squared, right? Then of course, remember that P is a vector. Because of that, we have not solved this until we know the proper direction. Now the direction depends on the compass rose, which will always start at 0 degrees and go around to 360 degrees. So in order to say that this points in the fourth quadrant, we know that it must be between 270 to 360 degrees. So if I use this as what I'll call theta, then I can find theta and subtract from 360 degrees. If I subtract backwards from 360 degrees, that will put my vector exactly where it needs to be in terms of proper direction. And so what I'm going to do is I'm going to say that the tangent of theta is equal to the opposite, which would be P1 prime in the y direction, divided by the adjacent, which is P1 prime in the x direction. That allows me to solve for theta. And then utilizing theta, I would say that phi, which is the proper direction of the green vector, starting at 0 and going all the way around to here, is phi. This is the proper direction of P1 prime. Phi would simply be 360 degrees minus theta. Now once I have all of that, that tells me what P1 prime is. P1 prime is a vector at a direction. Now, did I answer the question? Well, what was the original question? The original question was, what is V1 prime? Well, can I solve for V1 prime now that I have P1 prime? Of course, right? P1 prime is M times V1 prime. Now, of course, this will just use the magnitude in order to solve for that number, right? But then when I list velocity V1 prime, since this is not a straight line, it's not positive or negative in the x or the y direction, the direction of P1 is the direction of V1, right? And so what I have is that this would be a new number, right, which is simply P divided by M, but at phi in terms of direction. That is the final solution.